Now, if you saw a circuit like this, where you had two batteries, just using what you know about capacitors and resistors, you probably would be really confused. How can there be kind of two batteries there, right? And how can we like figure out some unknowns in this circuit, right? So we're given like EMF 1 is 28 volts. We don't know what EMF 2 is, right? So EMF 1, 28, I'll just actually write them. 28 volts, right? We don't know this EMF, but R1 is 6 ohms. 3, this is 3 ohms. R2 is 6 ohms. I1, we don't know R3, and I1 is 6 amps, while I2 is 4 amps, right? So we don't know R3 and EMF2. How can we figure that out just using these resistors and Ohm's law, right? Because think about it, if R3 is equal to like V over, so like if R3 is equal to V over I, what I are you going to use, right? Well, there's 6 amps here, and it looks like it's going that general direction, so maybe we put 6 amps there, right? Because look, 6 amps is going around here. What's the voltage? We do 28 volts. It's kind of hard to just do it based off what we know. We got to use Kirchhoff's laws. So Kirchhoff has two rules, and his rules basically are called the loop rule and the junction rule. The loop rule says, and I'm not going to go into a deep dive explanation because I want to make that video separate. I just want to show you how you can use them. So loop rule, the total voltage, right? If you take the sum of like all the voltages around a closed loop, it's going to be 0. It's a conservation of energy statement. And the junction rule is saying the current into a junction is equal to the current out of a junction. So I'm going to show you how we use these rules for a circuit like this. So just pretty basic in the grand scheme of things. So first of all, let's say we want to figure out EMF. Let's just say we want to figure out resistance 3. Well, we know from the loop rule that, yeah, the sum of all the voltages is going to equal 0. So you can choose what loop you want. There's really a couple loops you can do. You can say, okay, this loop, right? So the current, you can see 6 amps here, 4 amps here. So there's a loop here, right? Now what about, now this is kind of confusing, right? Because it's like, okay, there's current going here, but what about the current going here, right? Like there's going to be a loop this way, but it seems like there's current flowing out of here. How can there be current flowing out of here? What's the direction of all the current is basically what you should be asking yourself, because we have 6 amps this way, 4 amps this way. What about the current going through here? This is where you would actually use the junction rule, right? So the junction rule says that the current coming in of a current is equal to of a junction is equal to the current coming out of a junction. So the current coming into this junction right here, that's a junction, right? Because it's where 3 conductors meet up. The current coming in, and I got some black on my marker, but the current coming in is 6 amps. And we know there's 4 amps coming out of that current. Well, there's got to be 2 amps, right? In order for the conservation of charge to be true, there's got to be 2 amps coming out of here, right? So 6 amps has to equal 4 amps and the 2 coming in this way. So there would be 2 amps flowing into our guy right here. So is equal to plus 2 amps. Okay, so in that case, in fact, what we could really do, and then that 2 amps is going to come out here, and then we have 2 amps here, and then there's going to be 4 amps obviously coming through this wire, and then Kirchhoff's rule is obeyed once again, because we have 4 and 2 coming in, you got to have 6 coming out, and that is exactly true because we have 6 coming in. So that's what all the currents are looking like. Now let's say we want to solve for EMF2. We would use the loop rule in this case, right? So we would say, okay, if let's say you started right here, okay, and I'm going to just kind of show you conceptually what's going on with the loop rule. You're going to gain potential going through the battery, right? Because you're going to gain electrical potential energy. So whatever, when you're going through here, you're going to kind of go up. You're kind of gaining potential. So you're going to gain EMF2 amount of volts, right? I don't know how much EMF2 is. But as you're going through the resistor, you're going to lose some electrical potential energy. You're going to lose some electrical potential energy because your resistor is going to kind of take out, you can say, power, right? It's going to dissipate some power, dissipate some energy. You're going to lose a certain amount of voltage. How much voltage are you going to lose? Well, it's equal. Well, you can use Ohm's law in this case, right? You're going to lose I1 times R1. Awesome. So, and then minus, now I'm saying minus because when you go around this loop again, right, now you're gonna lose some potential to this resistor here. So with the battery, you were going up, then you're going down, then you're going down, and you have to be back to the same spot, right? So that's why the total is gonna equal, like when you sum it all up, it's gonna equal 0. Everything's back to the same spot. So we would do EMF2 minus I1 R1 minus I2 R2, right? We're doing I2 here because in that part of the circuit, it's going to be, you know, what's the word? Wait, what's the word? It's going to be, that's going to be the voltage, right? That's the current going through that resistor. That's why we say I2. So, hey, there you go. This isn't too bad because we know I1 R1 I2 R2. Hey, we just use EMF2 equals I1 R1 plus I2 R2. EMF2 is equal to, so I1 is 6 amps plus or times the resistance one, which is 3 ohms, plus now R2 is 6 ohms. So actually I2 is, what am I saying? I2 is 4 amps, right? And then we can use, and then we're gonna have we're going to have what are we gonna have? We're gonna have R2 is 6 6 ohms. Okay, I'm sorry, I was thinking to myself. So EMF2, this evaluates to 18 volts plus 24 volts. You're left with EMF2 is going to equal 42 volts. So that is the EMF of that battery or whatever. And we're going to assume, no internal resistance. 42 volts. Awesome. Okay, so now for R3, what you can do is, now for the loop here, a lot of people, you can use this as a loop, right? And I'm going to show you how that gets you the same thing. Now, that's kind of confusing because you're like, wait a second. There's a battery going this way, but then you're going into the positive. That's not usually how current works. That's true, but you can still use it. You just have to be careful with the signs. You can still use that as a loop. I'm going to show you the more intuitive way that you might have jumped to is using this whole loop, right? So using that loop rule, we can say, okay, the EMF1, you're going to gain some potential. So we'll say EMF1 minus, all right, so you're going to go all the way here, minus R1, I1 R1, right? Because that's going to be the voltage drop you space due to Ohm's law. And then you're going to go back up here, and remember we're going to do minus I3 R3, right? And we solved for I3 using the junction rule, so we know it's 2 amps. So from here we say, okay, EMF1 is, so we're solving for R3, right? So EMF1 minus I1 R1 is going to equal I3 R3. So EMF1 is 28 volts. I1 is 6 amps. R1 is 3 ohms. I don't know why that took me like 10 years to think about. Is going to equal I3, which is 2 amps. And then R3 is what we're solving for. So 28, this is 18, so we get 10 volts is equal to 2 amps. R3, which is going to equal 10 divided by 2, right? R3 is going to equal 5 ohms. I don't know. Yeah, hopefully you can see that right there. Just some algebra using the loop rule. So R3 is going to equal, what is it going to equal? 5 ohms. I don't know why it's taking me forever today to think about numbers. Okay, you can still use the loop rule for something like this. So you start at you start here, so you're going to gain potential and EMF1 amount of potential. Now you're going to go to EMF2, but okay, so if we thought about in this example where you're going up, right, to gain potential, if you're going backwards through the battery, initially, like for EMF2, you were also going up, but you're going backwards. So you're going to kind of go down. You're going to get a voltage drop. Now, current wouldn't do this, but conservation of energy would still apply in this case, which is why we can still do this strategy. I'm going to prove to you that, yes, you can really do this strategy. It will get you the same result. So EMF1 minus EMF2. And once again, you got to be careful, right? It's the same thing for a resistor. You're going backwards against a resistor, and how do I know I'm going backwards? Because remember, the current's going this way. So a resistor would give you a drop, but because you're going backwards, you're going to go up. You're going to do plus I2R2. And then once again, you're going, now we're going the regular direction again, right? Because this is the direction of current. So we're going to say minus I3 R3, right? Minus I3 R3, yeah. So then we're going to set that, I'll just do it here, all equal to 0. Okay, we're solving for R3 once again. So we can really do I3 R3 is going to equal EMF1 minus EMF2 plus I2 R2. Okay. Oh, and I don't know why I forgot. You also have to have the R3 here, right? IR. I just flipped it. So so let's plug in numbers. So I3 is, we solve 2 amps. R3 is going to equal, so EMF1 is going to be, it's given 28 volts minus 42 volts. Okay, this makes sense. And then plus I2 is 4 amps times 6 ohms. I swapped the units. 4 amps times 6 ohms. So this is kind of confusing, right? Because we have like negatives and stuff. This is going to evaluate to 24. So 24. Okay, well 24 plus 18, right? We saw it equals 42. I'm kind of being lazy here, but 28 is just 10 on top of 18. So if this plus this, or this plus 18 equals 42, and then we add on an extra 10 to get 52. And then you can also just verify in your calculator, 28 plus 24 equals 52, yeah. Which it does, and you can just kind of think about it as well. 2 amps, R3 is going to equal 52 minus 42 is just 10 volts, and then you get R3 is equal to 5 ohms, which is the same result. So you could choose your loop here, because conservation of energy will always apply, but it's not like you just gotta be careful, is what I mean, right? I like to use a loop when it's in the direction of the current. It just makes it easier, because then I know for sure this is having a voltage drop, this is having a voltage gain, but it's up to you. At the end of the day, you're the physicist, you're the person making decisions over at NASA, right? I'm sure NASA employees watch this. Thank you for watching this one. Bye.